Advanced Engineering Physics. Unit 2. Quantum Mechanics. Nanomaterials and Quantum Confinement. Nanomaterials are materials whose dimensions are reduced to the nanometer scale, typically between 1 and 100 nanometers. At these dimensions, the behavior of matter changes dramatically compared to bulk materials because electrons are no longer free to move over large distances. Their motion becomes restricted, leading to entirely new physical, electrical, magnetic, and optical properties. This phenomenon is called dimensionality reduction. Depending on how many dimensions are confined, nanostructures are classified into different categories. In one-dimensional systems, the material extends continuously in one direction while being confined to nanometer dimensions in the other two directions. Examples include carbon nanotubes, quantum wires, and conducting polymers. In zero-dimensional systems, the material is confined in all three spatial dimensions. Examples include semiconductor nanocrystals, such as cadmium selenide, metal nanoparticles, and quantum dots. Because of this extreme confinement, these materials exhibit properties that are completely different from their bulk counterparts. In ordinary three-dimensional solids, electrons can occupy a huge number of closely spaced energy states, which together form continuous energy bands. However, when the dimensions of a material shrink to the nanoscale, the allowed energies become discrete and quantized. Instead of a continuous distribution of energy levels, the system possesses individual energy eigenstates, separated by finite energy gaps. This change is described mathematically through the density of states. For bulk materials, the density of states varies smoothly with energy, whereas for nanostructures, it becomes a discrete sum of delta functions, represented as d of epsilon equals summation of delta of epsilon minus epsilon I, where epsilon I represents the allowed energy eigenvalues. Thus, electrons in nanostructures can occupy only certain specific energies, and this quantization strongly influences their electrical conductivity, optical absorption, and emission properties. Quantum confinement is the fundamental reason behind these discrete energy levels. Consider a one-dimensional quantum wire that extends along the z direction but is confined along the x and y directions. In this case, the electron is free to move along z, but its motion in the other two directions is restricted. As a result, the total energy of the electron is given by epsilon equals epsilon ij plus h cross square k square divided by 2m, where epsilon ij represents the discrete energies arising from confinement in the x and y directions, and k is the wave vector along the z direction. Therefore, the energy spectrum consists of a series of one-dimensional subbands. The density of states associated with each subband is inversely proportional to the square root of epsilon minus epsilon ij. Consequently, as the energy approaches the threshold of a subband, the density of states becomes extremely large and theoretically diverges to infinity. These sharp peaks are known as Van Hove singularities. They play a crucial role in determining the optical and electrical properties of one-dimensional nanostructures. In semiconducting carbon nanotubes, for example, Van Hove singularities dominate the optical absorption and emission spectra and are clearly observed in tunneling experiments. The most extreme form of quantum confinement occurs in zero-dimensional systems, such as quantum dots. Since electrons are confined in all three directions, they can occupy only completely discrete energy levels, similar to electrons in an atom. Proving for this reason, quantum dots are often called artificial atoms. A simple model treats the quantum dot as an electron confined inside an infinite spherical potential well of radius r. The allowed energy levels are given by epsilon NL equals h cross square multiplied by alpha NL square divided by 2m star r square, where m star is the effective mass of the electron and alpha NL is a constant determined by the allowed quantum states. The most important feature of this equation is that energy is inversely proportional to the square of the radius. This means that as the size of the quantum dot decreases, the energy levels move farther apart and the band gap increases significantly. Consequently, the optical properties of semiconductor nanocrystals can be controlled simply by changing their size. For example, cadmium selenide quantum dots emit different colors depending on their radius. Larger dots emit red light because they have a smaller band gap, while smaller dots emit blue light because they have a larger band gap. This size-dependent tuning of optical properties makes quantum dots extremely useful in light-emitting diodes, display technologies, lasers, solar cells, and biomedical imaging. Another remarkable property of isolated quantum dots is the existence of discrete charge states. Because the quantum dot is extremely small, adding even a single electron requires a finite amount of energy due to electrostatic repulsion. This charging energy is given by U equals E squared divided by C, where E is the electronic charge and C is the capacitance of the nanoscale dot is very small. The charging energy can become much larger than the thermal energy kBT. Under such conditions, electrons cannot flow continuously through the dot. Instead, current is blocked, a phenomenon known as Coulomb blockade. Current flows only when an external gate voltage is adjusted so that the energy levels of the dot align with those of the surrounding electrodes. Electrons then hop one at a time onto and off the quantum dot, producing periodic variations in current called Coulomb oscillations. In summary, reducing the dimensions of a material to the nanometer scale transforms continuous energy bands into discrete energy levels due to quantum confinement. One-dimensional systems exhibit Subbands and Van Hove's singularities, while zero-dimensional quantum dots behave like artificial atoms with tunable energy gaps and discrete charge states. These quantum effects are the foundation of modern nanotechnology and are responsible for many of the extraordinary properties and applications of nanomaterials in electronics, photonics, energy devices, and medicine.